Hello everyone, welcome to the IDS Vision channel. My name is Boris Duché. I'm a product manager here at IDS, and I will hold today's presentation, deep dive into sensor technology. Please keep in mind this presentation is made for advanced users, for engineers who want to get an in-depth understanding of the technology in order to optimize the setting of their camera for their application. Before we start talking about 3D, we need to have a quick talk about 2D images to understand the difference. So when we talk about a 2D image, we have to understand that each pixel is encoded with three values in the case of a color camera, with a single value in the case of a monochrome camera. These values are typically encoded in 3 times 8 bits. Each value represents one color channel, red, green, and blue, and your display, your monitor, will adjust the LEDs at the pixel level to display the appropriate color. This is how a 2D color camera works. When we talk about 3D, we work with depth maps. So how the 3D data is encoded within a depth map. So typically, for each pixel, you will have 3 values to encode the pixel. The values will be the X, Y, Z values in millimeter. Okay, so you have depth, but also X, Y information for each pixel. We like to display such an image in fake colors. It makes things easier to understand when we just look at the image. So in these examples that you can see on my screen, when the pixel is dark blue, it means that the pixel is far away from the camera. When the pixel is green, it means the pixel is close to the camera. This is only for visualization purpose. When you make your own algorithm, you will of course not work with the fake color image. You will work with the real depth map where each pixel is encoded with the X, Y, and Z value. This, the depth map, is a 2D representation of 3D data. There is another way to visualize 3D data. It's to use a point cloud. Let me show you how it looks like. I have this software that is called Cloud Compare that I use for visualization purposes. And in here, I have a 3D point cloud. So this is what you are more used to when you work with 3D. It's a real 3D file format. But keep in mind, sometimes we like to work with the 3D data represented as a point cloud, and sometimes we like to work with the 3D data represented as a depth map. Usually, when you make an algorithm that can operate on the depth map, it will make your algorithm go faster. And sensor cameras work according to the principle of active stereo vision. So I try to explain to you what stereo vision is first, and then we will try to understand what active stereo vision is about. Stereo vision, it is the way that your eyes work. How does it work? When you look at a point, the point will be imaged in both of your retinas. So they make a 2D image. And based on both of these images, your brain will compute some 3D information, some depth information. This is why we say that if you have only one eye, you lose the depth perception. If you close one eye and you try like this to touch your fingers, it's more difficult with only one eye than with 2 eyes. So this is the principle of stereo vision. Good news, it's not so different with cameras. They operate the same. So how does it work? Once again, this is passive stereo vision. You look at a point. The point is imaged in both of the sensors that make the stereo vision system. There is no brain into a camera, but hopefully the camera is connected to a computer, and you have the driver of the camera that runs on the computer, and the driver will compute the distance from the point to the sensor. We will go more in depth a little bit later about how this process works. The distance between the 2 monocular sensors that makes the stereo vision camera is called the baseline. It has a huge importance on the quality of your data. Usually when the baseline is larger, the accuracy of your point cloud is better. The angle between the two monocular cameras that makes your stereo vision system is called the vergence angle. It is, of course, important to have an overlap between the field of view. Let's take a look at an example how stereo vision works when applied to a camera. You will look at the same scene from two different points of view. The driver of the camera will take both left and right images, and we try to find for each pixel of the left image the corresponding pixel in the right image. If this algorithm is successful, then the computation of the depth map of the point cloud is successful. In the example that you see in my slide, you have a lot of homogeneous areas. You have a pixel that is white, surrounded by pixels that are right, and you look in the other image if you can find the matching pixel, and you have so many possible candidates, so many that the matching algorithm will not work. This is a limitation of stereo vision cameras. They don't like homogeneous areas. When you look at a pixel with local contrast, so the pixel is gray and the pixel on the right is white, and the pixel on the bottom is dark gray maybe. When you look for the corresponding pixel on the other image, it's pretty easy to find, so the matching algorithm will work. You will be able to compute the depth map. So passive stereo vision systems are limited when it comes to homogeneous areas. This is why sensor cameras are not passive stereo vision systems, they are active stereo vision systems. It means in between the two monocular cameras, we have added an additional component, which is a pattern projector, and that will just add some texture, some information on the image. Let's look at exactly the same example. Now I can see the same scene from the left and right point of view, but now my pattern projector added some texture to the scene, and it makes it much more easy for my matching algorithm to distinguish from one pixel to the other, because each pixel looks very different. So if I look on the right image, I have a pixel that is black, and the pixel on the top is white, and the pixel on the right is light gray. Can I find a corresponding pixel on the left image? Yes, I can, because each pixel is very different to the other, and you will understand a little bit later when we go in depth that you don't need to look for the corresponding pixel in the whole image. You will actually just look for a single line. So the computed depth map is much more dense, much more with less holes. Yet you still can see that some information is missing. Why is that? Because from the right and left point of view, you don't see the scene, exactly the same scene. Okay, you have some shadows area that are not located in the same place for the left and the right point of view. So these computed depth maps that you can see on my slide, I have made myself. It's not perfectly accurate, but the idea is to show you wherever you can see the shadows on the right image. If you go on the left image, you don't have the same information. Same thing on the left image, I have shadows in here, shadows on the left of my cup. I don't have the same information in the right image, so my matching algorithm will fail. This is a limitation of active stereo vision cameras. Hopefully, with Sensor, you can work with multiple cameras together and get rid of the shadows. Most of the camera families that we have in the Sensor product line operate according to the same principle, even though they have different form factors. So for each of these cameras, you have two monochrome sensors on the side, and you have a projector unit in the middle. Please remember that today's presentation is for engineers and want to give you in-depth understanding how those and sensor camera work. Now we will focus on the matching algorithm. We will understand the idea behind. I made a scheme to explain this to you. Here it is. On this scheme, you have two sensors, sensor S1, sensor S2. course, it corresponds to the two sensors of the two cameras that makes stereo vision camera. Two sensors and two optical center. And the optical center is a point within the lens where the light beams across will converge before reaching the sensor plane. The matching algorithm, what it will do, it will go through each pixels of the image number 1, and it will try to find the corresponding pixel in the image number 2. If it is successful, this matching algorithm, then the computation of the distance from X to P1, so from the point to the sensor, is pretty easy if your system is calibrated, meaning that you know the baseline, the distance between the two sensors, and you know the vergence angle. But this is computed in the factory calibration. So how does it work, this matching algorithm? You are looking at the point X. The point X is imaged in the sensor plane 1 at the pixel P1, and you try to look for the corresponding pixel in the sensor plane 2. Very cool thing. You don't have to look for all the pixels in sensor 2. You just have to look at a single line. This concept is called epipolar geometry, makes things much easier for the matching algorithm, of course. And this is our matching algorithms use this principle. So whenever we pass the image of sensor number 1, we just look for a single line on the sensor 2, and it makes the matching algorithm much more faster, of course. To compute the depth information, that is the distance from X to P1, the system needs to be calibrated, and it is very, very important that the calibration is accurate. So you know the baseline, you know the vergence angle, but try to imagine if that moves a little bit, from the production to the delivery of the camera to your place. I don't know, there is a problem, there is a shock onto the camera, and the vergence angle slightly moves. Then this value that we use to compute the depth is not accurate anymore. This is why in sensor cameras, the chassis is made in aluminum. We are very experienced in making these cameras, and the calibration is not lost. That's a very important step that we will discuss in the next chapter of this video. Now that we have a better understanding how the matching algorithm works, I would like to talk a little bit about the image rectification. This is an intermediate step that is performed by the driver of the sensor cameras before the matching algorithm actually. So the two images that come directly out of the two sensors that makes a sensor stereo camera, you have the left and the right images, and these images are not aligned. What does it mean? I mean, if I draw a line from one sensor to the other, you can see they are not perfectly aligned. But because my sensor cameras are calibrated in the factory, it means I can make a trick, an algorithm trick, so that both images align perfectly. Let me show you what it looks like. So these images in this slide is before the rectification. Now I will do the rectification to align perfectly my images. Here it are how it looks like. And now for each line of pixels of sensor 1, this line is perfectly aligned with the same line of pixels on sensor 2. It's very important, of course, for the matching algorithm, because it means that for every pixel of this line in sensor 1, I will look in the same line in sensor 2. Makes things much more easier, of course. What I want to show you in here is in sensor cameras, the chassis is made in aluminum and the calibration is extremely robust. These images I took with a quite old camera, and yet you can look after the rectification of images, the pixels are still, the images, are still perfectly aligned. This is what makes also sensor cameras very successful, because they are very reliable in the production line. So the calibration actually does not move even after years of usage. So once again, this is an intermediate result. You get the two images out of the sensor camera. You perform the rectification of the images so that both images perfectly align, and then the matching algorithm can go through each line of the sensor number 1 and find the corresponding pixel on the same line on pixel on sensor number 2. I would like to give you some explanation about the technologies that our customers like to use very often. It is called the FlexView technology. So far, we have seen how the stereo vision work when you work with sensor cameras. So you take a pair of images. The images are sent to the computer, and the driver will operate the matching algorithm to compute the depth information. With FlexView technology, we will not take a single pair of images. We will acquire multiple pairs of images, and we'll use these multiple pairs of images to compute the depth information. Of course, it only works with a scene that is static, not moving, but it gives much better results, and our customers like to use it very often. Let's explain how it works. So in the case when you activate FlexView when working with sensor cameras, the pattern that is projected by the projector will move. It will move, and as it moves, the sensor will acquire multiple pair of images for the 3D reconstruction. You will see it better in a few seconds when we start to play with the software. So here you can see the scene where the where the pattern projected on the scene is moving because we use the FlexView technology. We will acquire 2, 4, 6 image pairs, and based on these multiple image pairs, we will compute the depth map. And here you can see on the left the depth maps that you get when FlexView is disabled, and on the right when FlexView is enabled. So it gives you much better results with much lower noise level. Of course, it only works if the scene is static. Okay, so now we have seen how the theory, how does the camera work, how does the matching algorithm work, how the images are rectified. Now I would like to take a look at the software so that you can optimize the settings of the camera to match with your use case, with your application. If you watch this video, I guess you should be familiar already with the NX-View software that we provide with the sensor cameras. Let's open the NX-View software. Okay, in my case, I have 2 virtual cameras available. We'll open this one. And now it works. So what you can see in the NX-View software, you can see the rectified images. Remember that? So we'll open the full screen maybe. So you have the left and right rectified images where you have the overlapped patterns that is projected by the projector. You can see the depth map. So remember, depth map, each pixel is encoded with XYZ values in millimeters, depth map in fake colors. And you can see the rendered 3D view, in that case, with the monochrome information that is overlapped on nice scene. Okay. So what we would like to do right now is to get a deeper understanding of the parameters available in this software so that you can adjust them for your use case. So let's open the parameters view. And by default, you will have the easy to use view of the parameters. That means 5 presets, depending if you prefer to have a point cloud, very high data quality, but quite a slow frame rate, or you can choose to go dynamic fast. Click the play button. So in that case, the acquisition rate is much higher, but you will lose some accuracy. So dynamic scenes fast, static scene quality. There's a huge impact on data quality. It also has a huge impact on frame time. What is the difference from dynamic fast to static quality? Actually, you have 2 very important differences. One is the matching algorithm. We discussed the matching algorithm in detail in today's presentation. The matching algorithm can select between a few options when you work with sensor cameras. Some of these algorithms are extremely fast. Some of these algorithms are extremely precise. It really depends on the trade-offs that you want to achieve. Let's take a deeper look. If you hit the advanced options in here, under the stereo matching federation in here, you will find the matching method. That is the name of the matching algorithms that is used. When I choose to work with static scenes quality, the preferred matching algorithm is the sequence correlation. Usually, this is the one that gives one of the best results in terms of quality, but it is quite slow to operate. When you go to dynamic fast, it will use another kind of matching algorithm. It is a patch match. They all have some advantages and some disadvantages. Patch match is much faster, but also the region of interest that you make, the 3D region of interest that you work in, has no impact on the speed of the matching algorithm. So usually when you pre-select the static high quality, it will go with the sequence correlation, but also it will apply the FlexView technology. So the FlexView technology, you can see if it is applied or not in here, FlexView settings. So FlexView is enabled when you work with static scene quality. If you go dynamic scenes fast, FlexView is off because you want to take only one pair of images to acquire to compute the 3D point cloud. So once again, if I go back to static scene quality, now FlexView is enabled with 16 pairs of images for one 3D reconstruction. We can take a look if we want. Let's close it. If we go to the monocular image view, you have this slider in here that permits to go through all the images acquired via FlexView. So you can see, remember the project pattern is moving, and you can go through all the images to understand what is happening. Let's continue our journey to better understanding in sensor cameras and sensor software. So we discussed already about the matching algorithm and the FlexView technologies that permits to achieve high data quality or high frame rate. You also might be interested when you hit the advanced options in here. You might be interested into the post-processing parameters that you can see in here. The post-processing parameters, you can just have a look at the depth map on the left, play a little bit with the post-processing algorithm, and you have a quite obvious visual feedback, visual understanding what the parameter is about. Once again, we can adjust, for example, the median filter radius at the minimum, and now I increase this parameter to the maximum. And you can see at the edges of the depth map, the impact of the parameter. Okay. If you want in-depth explanation, in-depth understanding what each parameter is about, you just have to overlay your mouse on top of the parameter, click on the link, and you have access to the documentation, and you will have all the explanations that you need. I would say that most of the time, you don't need to have so much understanding. You don't need to play with them so much. Usually, you just hide the advanced option. You just choose the predefined set of parameters, and you should be satisfied with the results that you get. It's only in case you see a part is missing and you try to understand why this part is missing, and then you need to go into the parameters. In this very specific example, I'm a little bit disappointed because I don't see my object in here with the default preset. I try to understand why. And there, it is not because of the post-processing algorithm. It is because of the predefined 3D region of interest. So I'm quite sure that if I increase the depth range of my camera in here, yeah, that was the problem. So the maximum distance and depth range, those are parameters that define, let's say, a 3D area of interest. So the maximum distance will filter out any points that is more far away from this maximum distance. and the depth range will give you the width of the 3D region of interest. So you try to make the 3D region of interest as close as possible to your object or to your bin if you're working in a bin picking application, so that you can filter out any noise or any objects that you are not interested in. Another topic that I would like to address in today's video, it is the frame rate. A lot of customers come to us and say, how fast can you go with sensor cameras? And it's not that easy to answer that question because it depends a lot on your application. It depends a lot on the parameter set that you will use. I think you understood now that the end sensor will acquire a pair of images, send this pair of images to the PC, and on the PC side, the matching algorithm will be performed by the driver. In my case, the matching algorithm performed by my computer, it takes 1.3 seconds because I'm currently working on a laptop. It's not a very powerful configuration, and the matching algorithm takes lots of time. Remember, this is an N-Sensor C57, so 5 megapixel images for both left and right sensors. This computation of the disparity map can be increased by changing the matching algorithm. This we've seen already. Quick reminder, I'm here into static scene quality. If I go to dynamic scene fast, I decrease the computation time for the matching algorithm. Therefore, I increase my frame rate. But also, the configuration of my PC will have a huge impact. So currently, I'm working on my laptop. I think, yeah, I'm using the graphic card of my laptop. But if you have a more powerful graphic card, it will have a huge impact, and you can expect to diminish this computation time and to increase the frame rate of your camera. Also, like any other camera, one of the limiting factors is the exposure time of your camera. So by default, the exposure time is set to automatic. In the case of the N-Sensor C57, the projector unit is extremely powerful, which means you can work with quite small exposure time. So how do you adjust the exposure time? You can see your left and right images in here. By default, the exposure time is set automatically, but you can disable that, and you can play with the exposure time to try to have left and right images with enough contrast for the matching algorithm to operate. If your exposure time is too long, it will have an impact on the maximum frame rate that you can achieve. Okay, usually we leave this automatic, but it depends. In some application, you may want to set it fixed. Okay, if you want some help understanding the maximum frame rate you can achieve with an N-Sensor camera, it depends from one family to the other, but you can access the documentation. It will explain how to distinguish between the acquisition time and the computation time that is needed for the matching algorithm to perform to find the corresponding pixel for the left and right images. Last but not least, I would like to have a quick talk about calibration. So you understood during the first part of this presentation that it's extremely important to have a very accurate calibration. This calibration is done in the factory. The chassis of N-Sensor cameras is made in aluminum. N-Sensor cameras have been in the market for quite a few years now, so the calibration is extremely stable. Yet, you may want to check the calibration of your camera. This is a good habit to have. So you should have calibration plates sold to you by our sales team. And when you install the camera, it is a good habit when you install the camera for the first time to show the calibration plate to the camera and to go in the workspace calibration tabulation in here. Shows the calibration plate to the camera, and it's a recalibrate camera after mounting. This is an extremely simple process. You just have to click once, it will take an image, and it will just make a very light recalibration of the camera to make sure that you have the best achievable results. So this is a good habit to take. That concerns the intrinsic calibration of the camera. Another kind of calibration you may be interested in It is about changing the coordinate system of your point cloud. So by default, when you buy an Nsensor camera and work with it for the first time, it will look like this. Give me a second. By default, when you buy an Nsensor camera, the coordinate system is in here. You can see all the three axes, or at least you can see two. Yeah, you can see the three axes. By default, the center is on the left camera. Sometimes you like to change the coordinate system that you work with. Typically, if you make a beam picking application, you like to have the origin of the coordinate system in the middle of the beam, for example. So in that case, you will go under the workspace calibration tab in here, and you will hit the button set origin with calibration plate, and you just have to show calibration plate to your camera. It will be displayed and overlaid live in the camera images. I cannot show it right now because I'm using a virtual camera, and you will just hit this button and it will redefine the origin of your coordinate system. So this is one of the first things that you do usually when you work with an Nsensor camera. Here we are at the end of today's presentation. I hope that you liked it, that you learned a little bit of something. Keep in mind, first contact you have with the Nsensor cameras, you should stick to the 5 presets that you have. Very easy to use. It's almost a plug-and-play camera. And as you get more comfortable with the tool, you start to show the advanced option and you start to try to optimize the settings. Please remember that you have access to support at IDS, support team in Europe, support team in the US, support team in Asia. So how do you reach our support team if you face any problem? You just need to go to our website. You go to the IDS website, should be in your favorites already. You just hit support button in here, support and return, get technical support ticket. You will have to fill a form in here that gives some information. What is the project you're working on? And this ticket automatically will be forwarded to the support team, the closest to your area. Don't hesitate. If you feel uncomfortable to optimize the settings of your camera, ask the support team to organize a team viewer session. Usually for an experienced Nsensor user, it takes 5 minutes maximum to optimize the setting. And in 5 minutes, it can help you save so much time. And once you get comfortable with Nsensor tools, it will be for you also a few minutes to install the Nsensor camera. Thank you very much for attending this IDS Vision Channel meeting, and we hope to see you soon for another video. Bye-bye.